Students, for today's lecture, we are going to talk about the crystal lattice. So the crystals are items having long-range order in a periodic arrangement. So a typical example is this one, the crystalline silicon dioxide, where you can see the silicon atoms here connected with, in this two-dimensional projection, connected with 3 oxygen atoms. And one oxygen atom is connected with 2 silicon atoms. And this is so-called crystalline silicon dioxide or quartz, because you have a periodic long-range order of the crystal or of the atomic arrangement. So that in reality, if you see the crystal of quartz, you'll see tiny, tiny facets on the surface of your quartz, which corresponds to certain crystallographic planes and directions. And in comparison, you may have a so-called amorphous material as well. For example, the amorphous silicon dioxide here, which is usually called a glass. And in amorphous materials, you don't really have long-range atomic order, but may have short and medium-range orders. For example, although in this amorphous glass structure of silicon dioxide, you have some distortion of your lattice as compared to the previous page, where you have a certain periodic regular arrangement. However, you can see still that the arrangement of the items and the number of chemical bonds between the items are in general maintained. So in amorphous material, you still have some short and medium range order, but no long range order. So by definition, crystals are items or molecules which are situated in a repeating or periodic array over large atomic distances or long range order. And crystals have 2 major characteristics. The first one is the melting temperature or constant melting temperature, where at a certain temperature you have the breaking of all your chemical bonds and your solid crystal becomes a liquid. And the second characteristic of crystals is the so-called anisotropy, which means your properties of your material is depending on the direction. Okay? So that's a natural result of your crystal structure because you have a certain atomic long-range arrangement, and different directions will correspond to slightly different atomic arrangement, giving rise to your different properties, or anisotropy. So an important concept of describing the real crystal structure is the lattice and the basis. A lattice is a kind of a conceptual thing, where it indicates a collection of points called lattice points, which are arranged in a periodic pattern so that the surrounding of each point in the lattice are identical. And it's a kind of a logical thing where you have like spatial lattice points, and the basis is a real thing, which means a group of one or more items located in a particular way with respect to each other. And the crystal structure is actually the summation or the combination of lattice points and bases. So for example, here you have this 4x4 lattice points, and at each of these lattice points, you have this combination of 4 pins of different colors. And eventually, your crystal structure is this one, okay? In this 4x4 crystal structure, you still have this 4x4 lattice points. However, at each lattice points, you have a combination of these 4 colored pins. And that is the way the crystal structure is made. And this is your lattice points and motif. So this is another example. This is a real crystal structure. And this real crystal structure can be decomposed into a lattice and a structural basis. And in this particular one, this is a so-called face-centered cubic lattice, where you have corner items and you have 1 atomic lattice points in the center of each face. And then at each of these lattice points, you have this structural basis comprising of these 3 items. And the combination of the lattice and the structural basis made this real crystal structure. And an important concept is the unit cell, which is the subdivision of a crystal that still retains the overall characteristic of the entire lattice. And it is the smallest identical unit in the lattice. And it is usually a so-called parallel lepipase. And it has to meet several requirements. For example, it has to represent the symmetry of the crystal structure. And you can describe the geometry of the unit cell or the parallel lepipase by the edge lengths A, B, C here. So you have different edge lengths. And the angles formed between each of these axes. And to meet the requirement of the symmetry, and you only have, so mathematics can prove that you can only have 7 crystal lattices with different combinations of these edge lengths and edge angles. And in particular, they are cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, and hexagonal. Okay, so all these 7 crystal systems are found in real minerals. For example, fluorite, rutile, barite, rhodonite, and etc. The 7 crystal systems can be further divided into 14 possible basic crystal structural units or unit cell types. This is a mathematical requirement because the unit cell has to fulfill the following requirements. For example, it has to represent the symmetry of the lattice. It has the minimum volume, maximum number of equal edge lengths and interaxial angles, and the maximum number of right angles. Okay? So you can only have 14 different types of unit cells. So here I just show some typical crystal structures. For example, this is your copper face-centered cubic or FCC structure where the copper atoms are occupying each of these corner lattice points on a cube lattice. And then there is 1 copper atoms on each of the face-centered. So that's called a face-centered cubic or FCC structure. And for sodium chloride structure, the basic or the unit cell is still face-centered cubic lattice. However, you have 2 FCC lattices interpenetrating together, and you have a chloride FCC structure, you have a sodium FCC structure, and the 2 structures are having a relative displacement of this amount, so that you have a combination of 2 FCC structures forming this sodium chloride structure. A more complex case is the zinc sulfide structure, where you still have 2 FCC lattices for zinc and for sulfide. But the difference is that the 2 FCC lattices are relatively moving to each other by this 1/4 of your body diagonal. So this is a zinc sulfide structure. This is an example of body-centered cubic structure where you have your chromium occupying these cube corner positions, and in addition there is 1 additional chromium at the body center of your cube lattice. So that's a BCC structure. An interesting case is this one, cesium chloride. So you have your cesium atoms on the corners of this cube, and you have your chloride atoms in the center. And do you know whether it is a body-centered cubic lattice or not? The answer is no. It actually has a simple cubic unit cell. So essentially, the cesium and your chloride atoms, each of them are forming this simple cubic lattice. And 2 simple cubic lattice, when they interpenetrate each other, you actually have the cesium chloride structure. It looks like body-centered cubic, but it's not. It's simple cubic lattice. So for today, we have talked about the crystal lattice. Thank you very much.